students. Today we'll complete part 8 of Solid State, Chapter 1, Class 12 Science Chemistry. Let's start. Defects in solid. There is a saying that in this world nothing is perfect. Imperfection is the most common thing in everything. So the case of solid as well. Now, when we talk about the solid, it have many crystals in it. So if there is any imperfection in solid, it happens just because of the crystallization process. If the crystallization happens very fast, then it results in the amorphous solid. If it happens in the moderate state, then there is a chance of forming some imperfection. And if it happens very slowly, gradually, then we can expect a perfect solid, which is a very rare case. So today we are going to talk about the defect in solid, which is of two types. One is point defect, another one is line defect. Now when we talk about the point defect, it is basically about a point, some anomaly that happen around a point. And when you consider the line defect, it means that the whole row of the atoms or molecules or ion in the solid will have some anomalies. There will be complete defect. There will be a defect in the complete row or in complete column. Anyway, we don't need to bother about the line defect, but we have to consider the point defect as it is there in your course. So let's see what are the point defect. In the flow chart here, you can see some point defect categorized. One is impurity defect, second category is stoichiometric defect, and another one is non-stoichiometric defect. Now stoichiometric is something that is deal with the formula, with the whole number of atoms present in it. Stoichiometric defect can further be categorized into four types. One is Schottky defect, next is Frankel defect, next vacancy defect, and interstitial defect. We have to study detail about all this category. Next is non-stoichiometric defect, which is again of two types, metal excess defect and metal deficiency defect. So let's start with each category. Now first one is impurity defect. In this picture you can see a solid crystal is given with the cation sodium and anion chlorine. NaCl, NaCl, like that. The arrangement you can see here. Anyway, if you take the molten sodium chloride, or if you melt the sodium chloride, and in the molten state of the sodium chloride, suppose we are adding some strontium chloride, that is SrCl2, then it may happen that the cation strontium 2 plus will occupy the space for sodium plus. Now in strontium 2 plus, if one strontium 2 plus have to replace the sodium, then it will replace two sodium ion, because the charge need to be balanced. In electrical neutrality is important in the solid. So if one strontium is occupying the place of sodium, then two sodium cation have to leave its space. One space will occupied by the strontium atom and another will left vacant. The same happened here. So in this impurity defect, it happened due to some foreign particle, that is strontium, and this is called the impurity defect. So impurity defect, you have to remember that here foreign particle will cause the anomaly. Next is the category of the point defect. We have already seen the four category. One is vacancy defect, next is ion pair defect, that is commonly known as Schottky defect, next interstitial defect, and at last we get the Frankel defect. Second and fourth happen for the ionic solid. So we'll study these two together in terms of their comparison. And first and third, it happened for the non-ionic solid. second and fourth for the ionic solid, first and third for the non-ionic solid. So in case of second and fourth, electrical neutrality must be balanced carefully. Let's see the stoichiometric defect, point defect, stoichiometric defect, ionic solid. Why stoichiometric defect? Because here the number of cation and anion will not get disturbed. That's why it is called stoichiometric defect. Now in Schottky defect, you first check the figure out. In this part, you can see cations, anions, anion cations are arranged. There is some missing space. This is the space that is vacant. This is the missing space of, this is the space for a missing anion, and here you can see the missing space for a cation. So in this figure, what you are observing, we are observing that a pair of cation and anion is missing. So Schottky defect forms when oppositely charged ions leave their lattice site, creating the valency. That means if one cation is leaving its site, one anion also must leave its site. When the cation and anion they leave the solid, then what happens? The mass decrease because they have some mass and that is escaped, that was escaped from the lattice. So it always decrease in the, it always result in the decrease in density. So in Schottky defect, what we observe? We observe the decrease in density than the normal solid. One condition hold here. The condition is that the size of the cation and anion must be comparable. That means they must be of almost similar size, or you can say there must be less difference in the cation and anionic size. That means their size must be same. So in Schottky defect, it happened because one cation and anion get missing from the lattice site. It result in the decrease in the density. It happened when the size of the cation and anion are almost similar. One example is your sodium chloride. Then you can talk about calcium chloride, then cesium chloride, then silver bromide. Okay, these are the example of Schottky defect. Now let's understand what is Frankel defect. In Frankel defect, another name of Frankel defect is interstitial defect or dislocation of ion defect. In Frankel defect, the cation, here you see is the space for cation. The cation left its space and it occupies some interstitial place. That means dislocation of the cation happen here. But do mark here that in this case electrical neutrality is balanced because the cation is within the solid. It get displaced but it did not leave the solid. It is there only. So in Frankel defect there is no change in the density. The condition for Frankel defect is there must be large difference in the size of cation and anion. The cation should be small and the anion should be very much bigger so that the cation can easily occupy the void in the crystal. So that condition must be there. Example of Frankel defect are your zinc sulfide, then AgCl, AgBr. Okay, one thing is common between these two, that AgBr, okay, silver bromide is the type, is the solid that shows both Schottky defect and Frankel defect. Okay, so stoichiometric defect, in ionic defect we are getting two types. One is Schottky defect, another one is Frankel defect. Next stoichiometric defect is vacancy defect. Vacancy defect is very easy. You can see this line. Okay, it is a, suppose this is a solid crystal where atoms are arranged. Okay, now in this lattice you can see some vacant space. That means some atoms they left their site, so some vacancy created. It happened for the non-ionic compound. It don't happen for the ionic compound, it happened for the non-ionic compound where some atoms, molecules or ions they are missing from the lattice site. So some vacancy created and hence it is called as vacancy defect. Do remember, vacancy defect always result in decrease in the density because the atom is missing. They left the solid. So it always results in the decrease in the density. Next, interstitial defect. Interstitial means void or empty space in the solid. Check here, the solids, it's a solid where atoms or its particles are arranged properly. Now there are some extra atoms that are present in the interstitial site. This is your interstitial site where the atoms are occupied. Now in the solid we are getting some extra atom, and hence we can expect the increase in density. Interstitial defect also occurs in case of non-ionic solid, and it results in the increase in the density where some excess atom occupy the interstitial site. So that's all about your 4-point defect under stoichiometric defect. Stoichiometric means the formula will remain same. Next we'll see two categories of non-stoichiometric defect. One is your metal excess defect, another one is a metal deficient defect. Now in metal excess defect again we get two types. This part is a bit important. First category is metal excess defect due to anionic vacancy, and second one is metal excess defect due to the presence of interstitial cation. Let's understand the first one. One example we'll take here to understand the metal excess defect due to anionic vacancy. Suppose it's a crystal of sodium chloride. Okay. Now in sodium chloride, A plus will be your sodium plus and B minus will be your Cl minus. So let's think that it's Na plus Cl minus Na plus Cl minus crystal. Now if you heat the sodium chloride in excess of sodium vapor, then it happen like the chloride that is present in the bulk, that means the anion chloride that is present in the bulk, will move to the surface where sodium vapors are there. It will react there, it will react with the sodium over there and will form sodium chloride, neutral sodium chloride, and one electron. Now this electron will again come back, it will diffuse back to the bulk and occupy the vacant site of the chloride. So in this defect, what you got? You got an electron that trapped in the anionic vacancy. Okay. Now this center is called F center. F is ferrobenzoate, means it is a color center. The far benzoate is a color center. Now why it is a color center? The reason is this electron is a free electron. So whenever it will get energy from the surrounding, it will jump to the higher orbit. In the Bohr's orbital model, we have seen that electron jump to the higher orbit, and when electron return, after some time when the electron return back to the ground state, the extra energy captured released in the form of color. So in this case of imperfection, we get color. Okay, it will show sodium chloride. If we heat in sodium vapor, it show yellow color. Same as lithium bromide or lithium chloride, if we take and we heat it in presence of lots of lithium vapor, we see pink color. So different color happen just because of this F center. So metal excess defect due to anionic vacancy. Anionic vacancy created, which one is captured by electron. So some imperfection happen here and it is called metal excess defect. Here metal is more than the anion. Next category is metal excess defect due to the presence of interstitial cation. Now one example is zinc oxide. So here A plus is your zinc 2 plus and B minus is your O2 minus. Okay, in the solid the cation is zinc 2 plus and anion is O2 minus. Now when we heat the zinc oxide, it form zinc 2 plus plus half O2 gas plus 2 electron. Now oxygen being gas, it get escape from the solid. When you heat zinc oxide, oxygen escape the solid. So we are left with excess of zinc 2 plus and 2 electron. Now this zinc 2 plus will occupy and will get diffused and will occupy the interstitial site, and same as the 2 electron will also occupy some interstitial site. So in the lattice, due to the heating process, what happened? We are getting some excess metal ion, and hence it is called metal excess defect due to the presence of interstitial cation. Here metal occupied the interstitial site, and hence it is due to the presence of interstitial cation zinc 2 plus in the solid. So that is your metal excess defect. It is a non-stoichiometric defect because here the formula get changed. Earlier it was zinc oxide, 1 zinc and 1 oxygen, but when zinc 2 plus occupies some interstitial part, the formula is no more 1, but it will be something 1 plus x. Okay, and oxygen value will also will be something less. It is not 1, rather it will be 1 minus something y, 1 minus y you can suppose. So the stoichiometry, the formula get changed, and hence it is called non-stoichiometric defect. It is a non-stoichiometric metal excess defect. Hope you understood. So here two important thing. What is epicenter? Epicenter happen in case of metal excess defect due to anionic vacancy. You understood the phenomena. And this part, metal excess defect due to presence of interstitial cation, happen due to the heating and escape of the gaseous atom or molecule from it. The last non-stoichiometric defect, that is a metal deficiency defect. Now it is more or less similar to your impurity defect. In impurity defect we have introduced one foreign atom, but here it won't be the foreign atom, but it will be same kind of metal cation. So here we have considered some FeO. Okay, if in FeO iron is +2 oxidation state and oxygen is in -2 oxidation state. So it is a FeO crystal. Now sometime it happens that some of the Fe2 plus will get converted into Fe3 plus. Okay, now as soon as the Fe2 plus get converted into Fe3 plus, then how many Fe3 plus will be equal to Fe2 plus? How to balance the charge, how to balance the neutrality, electrical neutrality? The electrical neutrality will get balanced like 2 Fe3 plus is equal to or is equivalent to 3 Fe2 plus, because 3 Fe2 plus the charge is coming as 6, and on the other hand 2 Fe3 plus the charge is coming out as 6. So 2 Fe3 plus is equivalent to 3 Fe2 plus. So if one at iron 2 plus get converted into 1 iron 3 plus, or if you just assume 2 iron 2 plus is converted into 2 iron 3 plus, then 3 site will get vacant. Now in this 3 site only 2 site can get filled, because iron 3 plus is 1 atom only. So there is an excess vacant site that is generated, and that will get occupied by the electron. Now this kind of defect happened for the same type of iron, but the charge get difference. So here also stoichiometry get disturbed, and hence it is called the non-stoichiometric defect. So here you see, when you heat iron oxide in oxygen atmosphere, it form FeXO. X is less than 1. Vacant cation site are present. Which one is the vacant cation site? That is the site for Fe2 plus. Now charge is compensated by conversion of ferrous to ferric ion. Fe2 plus will get converted into Fe3 plus an electron. For every vacancy of iron atom, 2 ferrous ion are converted into ferric ion, provides the 2 electron required by the excess of oxygen. Oxygen will get will accommodate the excess electron. So that is your metal deficiency defect. Iron 2 plus converted into iron 3 plus. So one iron 2 plus have to leave its space to accommodate 2 iron 3 plus. Thus some anomalies happen and it causes the metal deficiency defect. So that's all for today. Hope it is clear to you. Thank you.